All right, so we're going to get started on 1.6 here, inverse functions and logarithms. So remember, functions are things that simply map from one input to an output. So you have something there and you give it some sort of input and it'll tell you some sort of corresponding output for it. And the thing that makes functions unique is that for every input you give it, you're only going to get one output. Now, multiple inputs can give you the same output, but if you give it one input, you're not going to get two outputs. You're only getting one output each time. So that is something that makes it a function and not just any other general mapping. And so I like to think of this as a machine. I have a machine that I give it supplies to, and it outputs some sort of product or something to it. I give it flour, and it outputs bread, something like that. Okay, and so that's what these functions do. They follow a set of rules. You give it an input, they give an output. Well, some functions are what is called one-to-one. So a function f of x is one-to-one. What this means is that not only do you only get one output for every input, but no inputs will give you the same output. So basically what we mean by this here, just in a picture, is if we have some sort of domain here and some sort of range here, so domain, range, for every x1 I put in, it's going to map me to a specific output. This would be f of x1, and x2 would map me over to some other point like this, f of x2, like that. And this is going to be one-to-one. Every single input maps to a unique output. This is 1 to 1. All right. Not one-to-one can still be a function. So we have some sort of domain or something here, domain, and some sort of range here. And what happens is we could put in an x1, and so this will still be a function, and it's going to map us to this point over here. But there could be an x2 over here that also maps to that same point. This is a function, but it's not 1 to 1, okay? It's a function, but not a one-to-one function. Okay, so what we need in order to have inverse functions is we need to have one-to-one functions so that the inverse itself is actually a function. Some functions that are not one-to-one, though, we can basically make them one-to-one, or at least make a version of them that is one-to-one, by basically limiting or restricting their domain. Okay, so we could do that so that we remove any of the parts that won't work. So like up this one up here, I might chop this part of the domain off by saying, oh, it's only from 0 to infinity instead, and then suddenly it becomes 1 to 1. Okay, so we can do something like that where we're going to restrict it and get it to be a one-to-one function. Note that the original function and the restricted function are not the same functions because they have different domains. Okay, they're not exactly the same. They may be very similar, have a lot of the same similar kind of properties, but they are not the same function. So first thing you need to do here, we need to learn how to decide if a function is one-to-one. So let's look here and decide if these functions are one-to-one. So first, f of x equals the square root of x. So this function looks like this, and it does that. And that's our f of x right there. And so it has a domain that goes from 0 inclusive out to infinity, and it is a one-to-one function. Essentially, the way you can test for this is what's right below here, the horizontal line test. But basically what that means is, is we have no repeating of the outputs. Next one, f of x equals sine x. So if we look at this function, remember sine of x looks something like this, and it does like that, and it keeps on repeating. Well, this is most definitely not one-to-one. So this one was 1 to 1. This one is not 1 to 1. Because if you look at this, the outputs repeat. So I may get a 1 right here, and I also get an output of a 1 right there. And if we kept going over here, there'd be a 1 here. And it just keeps going. So there's a lot of the same outputs. Say 0 repeats itself here a lot too. 0, 0, 0, 0. We have all these 0 values. So a lot of the output values are actually repeating. One of the things we're going to do with these, though, when we talked about in the last page, is you can actually restrict the domain. So if I were to do something like restrict the domain from negative pi over 2 to pi over 2, right, like that. So negative pi over 2 to pi over 2. Well, if we're only looking at just this part of the graph, well, then that part of the graph is itself 1 to 1. There's no repeating of values for the outputs, and then we could basically find an inverse for that new function that's restricted from negative pi over 2 to pi over 2. All right, so how can we check this? Well, we can do the horizontal line test. And so a function y equals f of x is 1 to 1 if and only if its graph intersects each horizontal line at most once. So if we look here, we can do a horizontal line test. Let's do it in light blue or something. We do a horizontal line test. No matter where we put this, we're going to end up only hitting that graph one time, not ever twice, so it will pass it. This graph, on the other hand, of sine x, look, we keep hitting the graph multiple times as we do the horizontal line test. So that tells you right there that this is not a 1-to-1 function, but we'd have to restrict its domain to make it 1-to-1. So right here, we see some 1-to-1 functions right there, and you can see they're passing the horizontal line test. Right here, here's a couple of functions that do not pass the horizontal line test, and they are not 1-to-1. So y equals x squared is not a 1-to-1 function, and so we can't do it. And the same thing with sine of x right there again. All right. Suppose basically what we want to start looking at here is inverse functions, and we want to suppose that f is a 1-to-1 function. So our original function is actually 1-to-1. On the domain, remember domain is inputs. Call that A, the A values we input, with a range of what we'll call B values that we get input. The inverse function, f to the negative 1 there, now keep in mind, this negative 1 is not the exponent negative 1. It's not f to the negative 1 power, so it's not 1 over the function, is defined by f negative 1, so f inverse we usually say, of b. Notice that was the output of the original function b. It's now the input of the inverse function, and it will equal the input of the original function. So if we take a function and we give it some sort of input value, and then we get an output, so we give it an input A and get an output B, if we reverse that, if we take the output, which was B, put it into the inverse function, it'll give us back A. All right, that's what inverse functions do. They undo the original function. So basically what this means is that the domain of the inverse function is the range of the original function, and the range of the inverse function is the domain of the original function. So basically when you find an inverse of a function, the domain and the range, they just switch, they flip-flop. The domain becomes the range and the range becomes the domain. So it makes it pretty simple to find these things. Note that the symbol f negative 1 again is read f inverse. It is not to the negative 1 power. Okay? So let's try this. Let f of x equal 2x plus 3 and g of x equal x minus 3. Find f of g of 5 and g of f of 5. So let's start by finding g of 5. And that's going to be plugging in 5 minus 3 over 2. And that's going to give us a value of 1. That's 2 over 2. That's 1. And then if we do f of g of 5, that's just f of 1, which is 2 times 1 plus 3, which is just 5. Okay? So note here that we ended up with the same output that was our input. Okay? So what I'm saying is note this 5 and this 5. So let's try the other one. g of f of 5. So let's find f of 5. That's going to equal 2 times 5 plus 3. That's going to be 13. That's 2 times 5 is 10 plus 3 is 13. And so now we want to do g of f of 5. That's just g of 13, which is going to be 13 minus 3 over 2. Plugging that into g. 13 minus 3 is 10. 10 divided by 2 is, how about that, 5. So you should note here that with these, if we input this into g and then take the result and input it into f, we got what we originally put in. And the same thing the other way. If we take and input something into f and then take that output and put it into g, we get back what we originally started with. What this does is it seems to imply that f of x that it is equal to the inverse of g of x. They are inverses of each other, or g of x equals f inverse of x. So that's what this seems to be saying. Now, normally, you would have to do a lot more than this because it might end up being true for one specific value. This is not sufficient to show that they are inverses, what we did here. It might be true for one specific value, but that doesn't mean it's going to be true for all values in the domains. So you have to be careful about this. But what this seems to be implying is f of g of x is just x. That is just whatever we originally plugged in. All right, so finding inverses. The formula for a function y equals f of x is given. Find a formula for the inverse of x. Identify f inverse of x. Identify the domain and range of f inverse. So notice here, this is an x squared function, which means that it's a parabola, and parabolas are not one-to-one, right? This is going to be something that looks something like this, going through plus 1. So it's going to look like that. This is not one-to-one, right? It fails the horizontal line test right there. It hits it twice, there and there. So we have to be careful. But notice this right here. X is greater than or equal to 0. What that essentially does is gives us a function that is just this part over here, right? It's only from 0 and greater, and this whole other part is gone. Right, so that's the actual function we're looking at. So make sure you pay attention to what the domain is. And in this case, because of that, this is 1, 2, 1. So that's our first thing we need to do. Check, is it 1 to 1? Yes, it is because of the restriction on the domain. So how do we go about finding the inverse? Well, it's pretty simple. We simply change f of x to y. So we replace, remember, f of x is just y, right? Y equals 1/2 x squared plus 1. So what we're going to do is swap x and y. So we'll make this x equals 1/2 y squared plus 1. So we're going to do that instead. And then we're going to solve for y. So we swap x and y. We solve for y. We solve for our new y there. And so that's pretty, x minus 1 equals 1/2 y squared multiplied by 2. 2 times x minus 1 equals y squared, and then take the square root of both sides. So we have y equals plus or minus the square root of 2 times x minus 1. Okay? But notice we have a plus or minus there. Well, which one do we end up wanting to go with? And we are going to want to take just the plus value, all right, because we don't have negatives for this. And so we'll get y equals just the square root of 2 times x minus 1, right? We're picking that plus value here in order to get our inverse. So what we get then is f. We can swap it back to our f inverse notation from our y equals. So, right, here's our next step. F inverse equals the square root of 2 times x minus 1. And if we go to graph that, it's essentially a sideways parabola. It's a square root function, but it is dropped down, right? And so what we're going to end up with is, this function right here. And so what it's going to look like is this here. It's going to be this square root function that does that, but it's shifted to the right by 1. And you'll note here that, take a look at this. If we draw in y equals f of x here, I'll do it on this dotted line. This is the identity function. Notice these are just mirror images of each other across that function. So this one was f of x. This one was f inverse of x. And they mirror image across this y equals x line right there. Okay? That's a very important property for these inverse functions. So the graphs of a function and its inverse are very closely related. That's what I was just talking about. The graph of y equals f inverse of x is obtained by reflecting the graph of y equals f of x about the y equals x line. And we just saw that on the previous page. It's just going to be true all the time. So we're basically taking every x value, every x and y value, and we're swapping them. So if we have the point 4, 5, it becomes, we replace it with the point 5, 4. We're swapping all x and y values to get this to work. And ultimately, what that ends up doing is if you have a point here, like the point AB, it becomes the point BA. You just swap x and y. And there you can end up drawing any graphs you want of inverse functions. Okay, so let's try here an example. Let f of x equal x squared minus 8x, and we want x to be less than or equal to 4. All right, that's our domain. And so find f inverse of x and identify the domain and range f inverse of x. So here, the domain for f of x, okay, the domain is negative infinity all the way up to 4 inclusive. That becomes from our x has to be less than or equal to 4. And then the range of this function is then going to be, we have to basically plug things in and see where it goes, is negative 16 to infinity. Okay, you should be able to figure out that is the range of this. And so what we want to do is now find the inverse. So find f inverse of x. And we start off again by replacing this f of x with y. So we're going to make that a y up there. And then we swap x and y. So this will be x equals y squared minus 8y, just like that. And then we have to solve for y. Well, that's kind of tricky to do here, so we have to actually go into completing the square. Hopefully you remember what to do there. We basically take this value that's right there. We divide it by 2 and then square. So basically what we have here is we have a square where we have that it's going to be a y by y square, y by y, and then we have a minus 8 by y square, and then we cut that square in half here, this one, this rectangle, not the square, the rectangle in half, and we end up with this right here. All right, and we have y by y and y by 4 and 4 by y, and then we have this little extra bit right here, remember this, and it's going to be 4 by 4. And so what we have to end up doing is adding and subtracting that 4 by 4, or adding it to both sides if you'd rather, so that it will work out. And so what we can do is make this x plus 16 equals y squared minus 8y plus 16. That's the 4 times 4. And when we do that, we can actually go through and start solving this. This part right here, we can make this on the right hand side. This is just going to become y minus 4 squared, all right, because 4 times 4 is 16, and negative 4 times negative 4 is 16, and negative 4 plus negative 4 is negative 8, equals x plus 16. We can take the square root of both sides, take the square root, the plus or minus, and you end up with y minus 4 equals that, and so I'm going to add 4 to both sides, and you get y equals plus or minus the square root of x plus 16, right? X plus 16, and then plus 4. Okay? Now remember, we have to flip-flop the domain and range. They switch. So for f inverse of x, the domain is the range of the original one. So that means it's going to be from negative 16 to infinity. Okay? And the range is going to be the domain of the original one, negative infinity to 4 inclusive. And if we look at that, we have to be able to get negative, we have to put input negative values and look at what we have to output. We have to output values from 4 down to negative infinity. Well, if this is a plus right here, if we use the plus version of this, we're going to get values that are in the positive side and larger. So what we're going to want to do is actually choose the negative x plus 16, right, plus 4, so that we get the proper range of outputs for what we're doing. So we're picking that negative value. So, oops, let me do this first. So f inverse of x is negative square root of x plus 16. And you can try it if you want. Try the plus versions. You'll see you're not getting stuff inside the range. Only the negative value will give you things inside this domain and range. Okay? So next is going to be the logarithmic functions, but I'm going to start that in a new video.